All right, Chapter 5 we're starting today, the definite integral, and we're doing Section 1, which is estimating with finite sums. Started off with a nice, oops, if I advance it. Okay, starting off with a nice simple example, as simple as I could make it. We have a train traveling 75 miles an hour for 2 hours, 7 a.m. to 9 a.m. And the question is, what's the total distance traveled? So if you just think about it, 75 miles per hour for 2 hours, 75 times 2, 150 miles. But if you also look at it, besides just your usual rate times time, you want to think about also a rectangle. So here would be a rectangle. I have a constant velocity of 75 miles an hour for 2 hours. So my height of my rectangle is at 75. The width of it is 2 hours. So if I think of my up and down as 75, my horizontal is 2, 75 times 2 would give me the area of this rectangle that would be in here if you picture drawing in some vertical sides here on either side. Thinking about why area of a rectangle makes sense to give you distance, you can look at units. That's usually helpful as well. So 75 is miles per hour. When we multiply it by 2 hours, the hours drops out, and I end up with miles. And so again, when I'm multiplying, I end up with my area of a rectangle giving me miles. The y-axis is always going to be our rate. In this problem, it was miles per hour. The x-axis is usually the time. Okay, let's take a look at a few other things. So the second part asks you, what if the graph of the velocity was a curve? Would the area under the graph of v of t still represent the distance traveled? The answer is yes. Okay, so if I go ahead and take a look at my picture here, let me get rid of this for a second. Okay, so if I look at my graph, I just started with a parabola, y equals x squared, or velocity is time squared, let's say. Let's say we're in feet per second for my velocity. And we're going to go from 0 to 3 seconds right here. So if I look at my graph, this would be 1 second down here, and 2 seconds right here, and 3 seconds right here. Well, I don't really have rectangles. I've broken it up into 3 sections, 1, 2, and 3, but they're not really rectangles. So what I'm going to do is just get an estimate as to how much area is underneath that curve and between the x-axis and the curve. I'm going to estimate it by pretending that there are rectangles down there, and I'm going to use the midpoint between these as the height of my rectangle. So between 2 and 3 at 2.5, if I come up to my function, I'm right here, and I could use that as the height of my rectangle as a somewhat decent, I guess, approximation. So here's a rectangle that would have roughly the same amount of area as the area under the parabola and above the x-axis. My second interval, the area in here, I'm going to estimate that by taking, again, the midpoint right here, halfway between 1 and 2 is 1.5, and I use that height right here as my next rectangle. So if I kind of go down, there's my second rectangle. And then the third one, well, gosh, it's going to be not very high at all. So if I find the middle and go up and just picture, my really short rectangle right there, a little hard to draw with my tool here. But anyway, those 3 areas, if I could add those 3 numbers up, I would get an approximation for how much area is under the curve, which would give me distance. So my first tiny little rectangle here, if I plug in 1/2 into my function, v is 1/2 squared, that would be 1/4, and the width of the rectangle, by the way, is 1. So if I'm doing area of a rectangle, length times width, the length would be v of 1/2, the width is 1. So I get a 1/4 there. My second rectangle, I'm using 3/2, the x value or t value of 3/2. So if I plug in 3/2 for t squared, I'd get 9/4, and the width again is 1, so 9/4 times 1. And the third one, halfway between 2 and 3, is 5/2. If I plug 5/2 in, 5/2 squared, I'd get 25/4. So I add these 3 rectangles areas up, and I get my approximation for how much area is under the curve. Okay, so that time was an example using the midpoint rectangular approximation method, or MRAM. So when I'm looking at my 3 pictures across the bottom, this is MRAM. In the middle here I have RRAM, and then on the far right I'll do left ram or LRAM. So for my first picture, that's basically the one that we just had on the previous example. So I would use the midpoint. Midpoint's right here. I try to picture the height going across right there. And the next one, midpoint's right here, and the height going across roughly, whoa, like there. So those are my rectangles. If I'm doing RRAM, then this first tiny little area down here, I'm going to actually look to the partition to the right. These vertical lines are what we call partitions. So if I'm looking for the area of this tiny little space in here, I look to the right. I see where my function is hitting the partition to the right. It's right here. And I'm going to use that as the height of my first rectangle. Okay, my second interval here, I'm going to look to the right, the partition right there, and go straight across and down. And third one, same thing, I'm using this one as the height. So here's my 3 rectangles. I would add those 3 up. You can tell the answer you get would be a little too big. If I'm doing left approximation method, then I am looking for the approximation of this tiny little area in here. I look to the partition to the left, which is basically a height of 0, meaning my first rectangle has no area. My second interval in here, I look to the left, and right here at a height going straight across, that's my left. And the third section here, I look to the left, partition to the left on that interval is right here. I use that height and go straight across. So I have 3 rectangles there. If I add up those 3 rectangles, my area is going to be a little bit smaller than what I actually have as area under the curve. Oh, I put in a little side note that really doesn't have much to do with anything. It's just if you ever wondered about square units, why we measure something as like feet squared or square inches or something like that. Even when we're talking about a circle, we measure it with square units. Kind of odd. But if you look back in history, it's because, again, they originally approximated area using rectangles. So units made sense for square units. Anyhow, so we're moving our calculus class here along to the third part of calculus, which is all about integrals. So just like you would think about derivatives, most probably would think slope of the line or slope of the line tangent to the curve. Derivative is a rate or a slope. Integrals you want to associate with area under the curve. Just like derivatives you think of slope, integrals you think of area. Okay. I put in one more problem here that's a bit more complicated. I took problem number 18 straight from the homework set, so 5.1, number 18 in the homework. And it tells us that we have a reservoir shaped like a hemispherical bowl with a radius of 8, and it's going to be filled with water to a depth of 4 meters. So a hemisphere means half of a sphere. So I actually chose to draw my semicircle or hemisphere on its side, just because my units will work out better that way, my x and y units. So this is supposed to be a semicircle. Sorry, it looks like a little bit bigger than that, but it's supposed to be a semicircle. And its radius is 8. So if I go ahead and just mark, let's see, right here, this would be 8 on the x-axis, and of course it would also be 8 on the y-axis since it's a radius, a circle. Okay, sphere. Now it says it's going to be filled to a depth of 4 meters. Well, again, my picture is sideways, so you have to kind of picture this is the bottom of the bowl, and as it's filling, there's more and more water going this direction, right? So if I draw in a line, it looks like about halfway, roughly right there, this is going to be at 4 on the x-axis. So the water is going to be all down in this section here. Okay, it's just turned sideways from my viewpoint. So part A, it asks you to estimate S, which is the water's volume, by approximating the water's volume with 8 circumscribed solid cylinders. Okay, so the previous examples we were drawing in rectangles and estimating area with rectangles. Now we're moving up a dimension and talking about volume, and we're supposed to be estimating volume. So we can't use a rectangle to estimate volume. So instead what we're going to do is we're going to draw in these same little partitions, and I won't be able to draw 8, but I'll just draw, oops, sorry, make that go away here. How do I do that? Ah! Oh my goodness. I'm not sure. Okay, maybe it'll just go away. Oh, so frustrating. Okay. Okay. Sorry. All right. Anyway, so looking at my partitions, I'm supposed to be drawing in 8 of these little guys. I don't think I can fit 8 in there, but picture drawing 8 little sections in there. And it looks like it would be a rectangle, but because it's actually three-dimensional, it has, if I slice it all the way down, each one of those little sections is not a rectangle, it's actually a cylinder here. And so instead of finding the area of a rectangle, I'm going to find the volume of that cylinder. Volume of cylinder is pi r squared h. So here my radius of my cylinder, if I picture going from here up, that radius would be whatever the height of the function is at that spot. And the height, this direction, well, if they're all evenly spaced, we're going from 4 to 8. That's 4 units across that we have, and we're supposed to be fitting 8 of them in there. So that makes each one have 1/2 as its height. So if I'm looking at pi r squared h, I'm going to have pi f of x squared times 1/2 as the volume for each one. So if I go to my next slide, here I'm figuring my pi r squared h, and if I start with 4, and then it goes to 4.5, and then 5, all the way out to 7.5. There should be 8 numbers listed in here. If I have 8 cylinders, I add them all up, do the math, come out with my answer. So again, pi r squared h for each one of the cylinders. If I go backward, I'm supposed to be also thinking about the height. So it did say 8 circumscribed solid cylinders. So circumscribed means basically I need to draw in the rectangle so that it's got a little bit of height above the actual area. This is looking very messy. Sorry, let me try to erase some of this. Let's see if I can make that look any cleaner. All right. So here we are. So we drew it in at 4, and then we were drawing in these partitions going across. I'll just draw a couple, maybe it'll look neater. So it looks like I'm going to have to do a left approximation if I want my my little slices to be circumscribed. Right, so it's starting on the left side. So that's why we started at 4 and we went all the way to just before 8, right, 7.5. Okay. The second part asks you to find the difference between the actual volume and our estimate as a percent or percentage of the actual volume. Okay, so in part B here, when we want a percent, it's part over whole. So when I look at V minus S, whatever the difference is, divided by the actual volume, that will give me my percent. So they flat out told us what the volume was, the exact volume is, and if I subtract then what I'm getting basically from part A as my estimate, absolute value, our estimate is actually going to be a little bit too big, right? So this number is bigger than that number, and then divide by my total volume that they gave me, I'll get a percent. Okay, so we've reached the point where you try one for yourself. So this practice problem, you want to pause here, and then I have one more slide where I show you the answer. So go ahead and hit pause, and once you're done working it out, go ahead and play it again. Okay, so for this example or this problem, it was about cardiac output, and it started with 2 seconds and went up to 24 seconds. The question didn't actually say whether to use the right rectangular approximation method or left or midpoint or what. So I just went ahead and did both of them, so you could do it either way. Due to the shape being kind of symmetrical, it turned out that the left and the right came out the same. But if you're doing left, you start at 2 and work your way across to 22, that's second to last. If you're doing the right side, you start at 4 and work your way all the way across to 24. Hopefully, if looking at all the details, it makes sense to you. Cardiac output, that's the same thing. You're just going to follow along like what we did on the previous example. And you set up your fraction, make sure you end up with liters per minute.